Hello, everyone. My name is Amaan Rahman, and I'm part of the Computer Aided Design Lab at the Georgia Institute of Technology. Today, I'm excited to present our work on modeling and design methodology for backside integration of voltage converters. In this research, we explore a novel approach to maximizing the utilization of the substrate's backside for advanced monolithic 3D integration, a concept we refer to as the functional backside integration. By leveraging this technique, we aim to enhance power delivery efficiency and overall system performance at next-generation semiconductor designs. Before delving into the details of our methodology and findings, I'll first outline the structure of my presentation. I'll begin with the motivation behind our work, which is broken down into two parts. Towards functional backside integration, where we discuss why we should take advantage of backside real estate to realize and improve monolithic 3D integration, followed by an overview of how we implement our methodology. We then delve into what tungsten-doped indium oxide or IW back-end-of-line devices are and how they enable functionality in the backside. Then I'll discuss the design, verification, and end-to-end development process of backside integrated voltage regulators, concluding with an evaluation of their impact at the on-chip level. As semiconductor technology scales to smaller nodes, power delivery challenges such as higher power density and increased IR drop become inevitable. The increasing routing complexity in advanced nodes result in interconnects with greater parasitics, which worsen IR drop and signal integrity issues. In modern high-power low-voltage designs beyond 8 nanometer technology node, the tighter power supply margins imply slight voltage fluctuations can easily cause instability or even chip or device failure. This issue is even more exacerbated in monolithic 3D and heterogeneous 3D designs where higher integration density amplifies power delivery constraints. A promising solution to counteract these constraints is the backside power delivery network, where we decouple the power delivery network from the front side and bring it down to the backside underneath the substrate. In fact, major semiconductor foundries have already announced plans to implement BSPDN in their 2 nanometer technology nodes. As a result, moving the power delivery network down to the backside has several benefits, such as improved power distribution, leveraging lower resistive backside metals, which reduce IR drop hotspots, as well as reduced routing congestion, as power and signal routing are decoupled, which will also improve PPA of integrated circuits. However, despite these advantages, a standalone BSPDN does not fully solve all power-related challenges, due to the fact one key issue is underutilization of backside, as backside metal layers are primarily dedicated to power routing. Additionally, voltage noise from off-chip components will not be accounted for as much with on-chip backside power delivery networks. So we have to think a little bit more out of the box how we can tackle off-chip parasitics and off-chip IR drop as well. Therefore, additionally, we like to introduce the fact that if we want to fully leverage backside real estate, we have to explore integrating and introduce back-end-of-line tungsten-doped indium oxide transistors, which enable full backside integration or functional backside integration. Using these back-end-of-line devices, we can realize more further power stability using voltage regulators that are fully integrated into the backside. Our contributions can be broken down into three folds. We first propose and characterize backside IVRs with the novel back-end-of-line tungsten-doped indium oxide transistors. Secondly, we developed our process design kit to characterize these back-end-of-line transistors and to fully design and verify our backside IVRs rigorously based on commercial technology node. Thirdly, we established an end-to-end EDA flow for dynamic power integrity analysis when we integrate voltage regulators in our PNR design block. In the bottom, we see our EDA flow broken down into 5 stages, where the first stage is our traditional placement and route flow, where we effectively this time partition the design into front side and backside, where the backside is purely for power delivery and the front side is purely for clock and signal routing. Then, given our current demand information of our benchmark, we leverage this information to load our voltage regulator to optimize the parameters of our IW devices and our capacitor to get an initial understanding of what we're working with. And we repeatedly tune this till we have reached a desired outcome. Then, given our specifications, we do physical design, layout of the backside IVR. We go from the entire DRC to LVS to parasitic extraction flow using our custom backside PDK. Then we integrate our physically designed IVR into the backside, sandwiched between our backside PDN, partitions, where we partition based on input power domain and output power domain of our voltage regulator. Then we do the full characterization of our on-chip dynamic IR drop and power integrity impacts using voltage regulators in the backside. And if we have achieved the worst case IR drop of 10% of VDD, then we have satisfied our goal. And if not, we have to go back and reevaluate. In order to characterize our backside voltage regulator, we need to first understand how we integrate the back-end of line devices in our metallization stack. These special back-end of line devices, or tungsten-doped indium oxide devices, allow for complete back-end of line integration, given that their process temperature can be up to 250 degrees Celsius. And since they are functionally N-type devices, we have to compensate by leveraging their enhancement and depletion mode operations to allow for proper IVR design. On the right, we see that we integrate the IW devices between the first backside metal layer and the second backside metal layer. And the capacitor layers, CBM, capacitor bottom metal layer, and CTM, capacitor top metal layer, are actually between MB2 and MB3. Given this holistic setup, we have now been able to design our backside PDK and also our backside IVR as a result. Our IW devices are initially characterized as Verilog A model cards, and the Verilog A characterization is actually based on true manufactured IW devices and their constants, and as a result, the Verilog A models are fully calibrated. We can see in the schematic on the bottom right that our IVR follows a switch capacitor architecture, which completely gets rid of the inductor, which is the main reason why we can't integrate fully on chip if we use inductors. So we use a switch capacitor architecture. The first transistor is a depletion mode type IW device, where the rest are enhancement mode. And the green path represents the charging of the flying capacitor, and the pink arrow represents the discharging of the capacitor. And this happens in switching intervals, since the clock inputs, clock 1 and clock 2, are out of phase by exactly 90 degrees. So our goal is to effectively make sure that we output 0.7 volts given 1.4 volts, since this is a 2-to-1 voltage conversion architecture. And we're trying to maximize efficiency, but we're also trying to maximize power density. But we can't maximize both, and because of that, there will be trade-offs, since they're indirectly proportional to each other. And we're also trying to minimize the output voltage ripple at steady state, and also make sure that the minimum voltage is at least 0.7 volts, so we can power up the standard cells appropriately. So at the end of the day, we come up with two types of designs, baseline and optimized. The baseline has been naively sized based on the capacitor, and we're trying to basically compensate for the switch capacitor's inefficiencies by sizing up the capacitor as large as possible, given our on-chip footprint. But for the optimized case, we try to leverage a smaller capacitor, but smartly connect multiple IVR units that are weakly efficient to improve their efficiency altogether. Given our characterized backside voltage regulator, we need to physically design the voltage regulator. In order to do so, we require a process design kit in order to rigorously design and verify our regulator layout. Unfortunately, there does not exist a backside PDK, so we develop our first novel backside PDK, leveraging commercial technology nodes, specifically 65 nanometer technology node, for the primary reason that we want to follow relaxed design rule constraints. Additionally, we create an automatic P-cell generator, or parametric cell generator, such that we can easily generate GDS2 layouts of our primitive devices, which are IWO and MIM capacitor devices, so that we can repeatedly iterate through different layouts as fast as possible. Given our PDK is fully compiled, we leverage Cadence Virtuoso to do schematic and layout design, and we use Siemens Calibre to do DRC, LVS, and then we use Synopsys Star RC to do parasitic extraction. Given that we have physically designed our voltage regulator, appropriately passing DRC, LVS, we then integrate our BSIVR into our benchmark. The benchmark we work with is OpenPython, which is an open source single core RISC-V CPU. And our standard cell and memory libraries based on our 3 nanometer in-house PDK for PNR, and they incorporate buried power rails as well. Given this, the current demand of these advanced technology node standard cells and memory cells are almost 1 amp, and the largest current demand is 670 milliamps. As a result, this is quite rigorous for a switch capacitor to handle. So therefore, we have to understand how we can optimize and work around it. So we have a baseline and optimized case, as discussed before, where the baseline tries to compensate for its inefficiencies by sizing up the capacitors, by maximizing the size of the capacitors, whereas the optimized case leverages the fact that we can have smaller weakly efficient IVRs in parallel and have their clock signals out of phase such that we can maintain the capacitor charge as long as possible. Therefore, the output ripple will be very small as 10 millivolts, as we can see here clearly. After we have fully verified connectivity of our voltage regulator to the entire on-chip design, we compare the baseline and optimized backside IVR design cases with no IVR case, which is just backside PDN. We see that our backside IVR baseline case has actually increases in worst case VDD droop, on-chip VDD droop, by about 50%, whereas the optimized case actually reduces the on-chip VDD droop by 50% compared to the backside PDN case with no IVR. And this just shows that the importance of constraining the IVR not solely on current load demands and meeting efficiency requirements, but also that we are physically constrained at the on-chip level. We can't just naively size up the capacitor, and we have to ensure we can maximally utilize the backside as much as possible. We've additionally showed that using an interleave structure with out-of-phase clock inputs significantly improves the power integrity effects at the on-chip level. In fact, we see also increased power density gains as well for a given target efficiency of about 60%. And we also meet our dynamic IR drop requirement for the optimized case, which is 10% of VDD. Both IVRs are operating at 400 megahertz. So the end-to-end power integrity simulation takes about 5 minutes compared to full end-to-end SPICE simulations, which would take significantly longer, especially that we're working with 300,000 standard cells for this single core configuration. Conclusion, our work can be broken down in 3 folds, where we introduce the first novel back-end-of-line fully backside integrated voltage regulator, leveraging back-end-of-line tungsten-doped indium oxide devices. We develop a novel backside PDK to rigorously physically design and analyze our voltage regulator and evaluate it as appropriately as possible based on commercial technology nodes. And we have a supported flow from DRC to LVS to parasitic extraction. Additionally, we also establish a complete end-to-end EDA flow to analyze the on-chip power integrity impacts when we introduce back-end-of-line voltage regulators, especially in the backside, and we have to co-design the power delivery network to work around with the voltage regulator as well. However, there are some shortcomings of this work, and as for future work, we want to rigorously analyze the off-chip and on-chip power integrity impacts of fully frontside and backside back-end-of-line IVRs to realize what are the trade-offs when we put IVRs also in the front side and how they impact the off-chip power integrity when we account for microbump parasitics, C4 bump parasitics, and interposer parasitics as well. Additionally, since we're introducing switching devices in the back end of line, it will be also very interesting to analyze the thermal integrity impacts. So this is also our future work. Thank you for listening.